momentum. Although only moving objects possess momentum, this concept is very similar to inertia. You may remember this from a previous tutorial. Momentum definition. In a way, momentum is the motion equivalent of inertia. A large moving object is more difficult to stop than a small moving object. Remember, an object in motion tends to stay in motion. Momentum describes or quantifies this tendency to keep moving. Momentum formula. Momentum is a product of mass times velocity. Thus, momentum, p, equals m times v. V for velocity would be in meters per second. M for mass would be in kilograms. And momentum is the variable p, which, as we will see, was typically in kilogram meters per second. Substantial momentum. A bullet may have a large momentum even though its mass is very small. This comes from the fact that the bullet has a very high velocity even though its mass is small. On the other hand, a tanker ship may have a large momentum even though its velocity is very small. This comes from its mass being very large in spite of the small velocity. Changing momentum. Obviously, all moving objects can eventually be stopped. Thus, their momenta are changed. This is usually accomplished by changing the velocity of an object, maybe by a push. Changing momentum with force. To change the momentum of an object, you must apply some force to it. Consider a push. This force could be applied over some time period. This could be a very short time period, which would be a very quick push, or it could be very long time, which would be equivalent to a very gradual or gentle push. Impulse formula. Impulse is equal to the product of force times time. Impulse will use the variable j. This is typically in kilogram meters per second. Force is typically in newtons, and time typically in seconds. Impulse observations. Impulse can also be defined as a change in momentum, delta p. Maybe you notice that the units of momentum and impulse are the same. This makes sense since impulse is just a change in the amount of momentum. Thus, they really are the same quantity, so they should have the same units. Impulse and momentum formula. Since impulse is defined as a change in momentum, it can also be written as F delta t equals delta mv. In either case, the delta is the change in time or change in momentum. When an object's momentum changes, it's usually the velocity that does the changing, not the mass. It's much easier to change the motion or velocity of an object than to change the amount of stuff in the object, although that can occur. No bounce interaction. Imagine a ball is falling towards the ground. It would take some change in momentum or impulse to stop the moving object. As the ball is falling towards the ground, it's got a mass m and a velocity v. Thus the momentum of this ball is mv. As it hits the ground and stops, now it's not moving. No velocity, no momentum. So in this case, the momentum changes from mv to 0. That's a change in momentum, delta p, of mv. Bouncing interaction. Consider a slightly different case. It would take even more impulse to stop the object and then make it ricochet in the opposite direction. Again, the ball is falling downward, mass m, velocity v, but this time, because direction is important, we'll make it negative for downward. As it hits the ground, this time it bounces upward. Let's imagine it bounces up just as fast as it was going down, so now its momentum is plus mv. This change in momentum to go from negative mv to mv is a change in momentum of 2 mv, twice as much of a change as before. Impulse example. During a rainstorm, drops come straight down with a velocity of negative 15 meters per second and hit a car roof. The mass of the rain hitting the car is 0.06 kilograms per second. Assuming the rain comes to rest when it hits the car, how much force is exerted on the car roof by that rain? Solution. Begin with our impulse formula. Ft equals delta mv. We're looking for force. In this particular example, instead of delta v, we might choose to use Vf minus Vi, which is the change in velocity. Calculation. With our previous formula, substitute the known values for mass, time, final velocity, which is 0, and our initial velocity, which we must keep as negative 15. Calculating with these values gives us a force of 0.9 kilogram meter per second squared. This is 0.9 newtons. This is the force that's acting on the rain, an upward push to bring it to a stop. The force on the car must be in the equal and opposite direction, Newton's third law. So the force would be negative 0.9 newtons. Additional question. If the raindrops were frozen with the same mass and velocity, if they hit the car and ricocheted upwards, how would that affect the force on the car? Be sure to consider the direction here. Because they would be changing their momentum more, due to the larger change in their velocity, a greater impulse would be required. Thus, more force would be applied to the car. This is why frozen